So now we are ready to calculate the inductance of coaxial line section, which is L long. For this, we can go back to our school days and find that the flux density B was proportional to the current and reverse proportional to the radius of this problem. And what we need to do is we need to basically integrate the flux that is flowing through the area between the internal conductor and the outer conductor. So the radius of the internal conductor in our example would be A, and the internal radius of the outer conductor will be B, and we basically need to integrate the flux that is flowing between A and B. And to do that, we know that the area will be the product of the length of this area multiplied by the radius. And what we do is we find phi by integrating the flux density over the area. So you have the integral. The integral is going from A to B. And what we find out is that the flux is proportional to the current, to the length of this section carrying current, and to the natural logarithmus of B over A. And now, when we have this connection between phi and I, as we have established before, we are ready to calculate the length or the normalized length to we are ready to calculate the inductance or the normalized inductance to unit length. And basically what we find at the bottom of this slide is that the normalized inductance per unit length will be mu0 over 2 pi multiplied by the natural logarithmus of B over A, and the result will be in henries per meter. So we need to understand that this example is calculated for infinitely long line, and that's why we can take this simple or relatively simple equations and use them to get simple result. And now we are ready to see some numbers that will help us understand and compare to what we know from RFIC and see the differences. Okay, to complete our coax inductance example, we will take a numerical example because we really want to feel in our hands the nanohenries that we will get from a coaxial line section. So to do that, we can take just a simple example of a coaxial line that is 50 ohm, and we will develop some numbers that we can get from that. So the impedance of a coax is given at the top equations that we can see here, and we see that it's proportional to or reverse proportional to the square root of the epsilon r of the coax line, and to the log of B over A, where B is the outer radius conductor and A is the inner radius conductor of this coax. So if we use 50 ohm, which is a very common characteristic impedance in RF design, and we also assume that epsilon r is 4, just to simplify the calculations, we can find that the natural logarithmus of B over A is roughly 1.667 or 1 2/3. And finally, we can use this number of 1 2/3 in the equation that we previously derived for inductance over unit length, and by using the right units, we can find that the inductance per millimeter of a coaxial line or infinitely coaxial line will be 0.33 nanohenry per millimeter, which is in the same order of magnitude that we will find in RFICs, just a little bit lower, and we will explain it later on. We need to understand that this result is depending on the fact that this problem has a ground. The coax has an outer conductor that serves as a ground, and grounds really reduce inductance, as we will show later on. So basically, we have a very simple example here that will later on help us feel better with empiric equations for inductance calculation that can be found in many books, but it's sometimes hard to understand how these people derive them, and if we don't have a feeling to the magnitudes of these inductances. So this simple example really sets the basics to later on acceptance of these empiric equations that we will meet later on.